Hi, in this video we are going to talk about the concrete implementation of the maximum flow Edmonds-Karp algorithm. So, let's create a new Java project with the name, for example, maxflow. Okay, and I'm going to create several classes. The first class is going to be the Vertex. The package name is going to be com.myname.maxflow, whatever. This vertex is going to represent the vertices in the flow network. We are going to have edges that's going to represent the edges in the flow network. We are going to have the flow network basically. We are going to have the class, for example, Ford Fulkerson. I could say that the class name is Edmonds-Karp, but whatever. Basically, it's going to be the Ford Fulkerson, because the Ford Fulkerson algorithm, as we have discussed in a theoretical section, is quite easy. It's like the specification. We just have to find the augmenting path, and then we have to increment the flow in the original graph. So we have the original graph, and we have the residual graph, and basically we have to find the maximum flow. The Edmonds-Karp algorithm just states that we have to use breadth-first search as a graph traversal algorithm in order to find the augmenting path. Okay, so we have the edge, flow network, Ford Fulkerson, vertex, and of course an app.java from where we are going to test our application. The vertex is going to be quite straightforward. We are going to assign an integer ID to all the vertices. We are going to assign a string name to all the vertices, and we are going to store a boolean to check whether this given vertex has been visited or not. We have to do a breadth-first search, and in a breadth-first search we have to check whether we have visited a given node or not. In the vertex constructor, we just have to get an integer ID and a string. So we have to initialize the ID accordingly and name accordingly. Okay, this.name is equal to the name. Then I'm going to override the toString method. Okay, I just have to return this.id, for example, plus some spacing, this.name. Okay, and anyways, I'm just going to right click and source, generate getters and setters for the ID, the name, and the visited. Okay, Ctrl-Shift-F to auto format, and that's all about the vertex class. What about the edge class? We are going to have the same implementation as we have seen for the shortest path algorithm. So basically we store a reference to the from vertex, so the starting vertex, another vertex for the target vertex. Okay, maybe this is not the most memory efficient implementation, because usually we just have to store a reference to the target vertex. But anyways, I like to specify the from vertex, so every edge has a starting vertex and an end vertex, from vertex and target vertex accordingly. Okay, private final double, or it's not going to be final, it could be final, but whatever, the capacity. Okay, it could be final because the capacity is not going to change in the course of the algorithm, and we just have to have a double flow. It cannot be final because the flow can change from iteration to iteration. Maybe I'm going to make it final just to make sure that it's not going to change. Okay, and in the edge constructor we just have to specify the vertex from vertex. It's quite a stupid name, from vertex, but whatever. Target vertex. Then we have to specify the double capacity. Okay, and basically, oh sorry for that, it is a E like this. This dot from vertex is equal to the from vertex. This dot target vertex is equal to the target vertex. This dot capacity is equal to the capacity. and we have to initialize the flow to be 0. Okay, the field variables are going to be initialized to 0 at the beginning, but just to be sure, it's going to be 0 at the beginning. We initialize the flow to be 0 for every single edge. I'm just going to override and create another constructor. It's going to get an edge. Okay, and first I'm going to generate the getters and the setters. So right click, source, generate getters and setters for the capacity, flow, from vertex, target vertex. Because I would like to set the from vertex, this dot from vertex is equal to the edge dot get from vertex. Okay, this dot target vertex is equal to the edge dot get target vertex. Okay, this dot capacity is equal to the edge dot get capacity, and this dot flow is equal to the edge dot get flow. Okay, so sometimes we would like to initialize a given edge according to a new edge. Okay, then I'm just going to have a method. First of all, let me override a toString method. I'm not sure whether we are going to use it or not, but anyways, I'm just going to return the from vertex plus some spacing plus the target vertex plus the flow, for example. So flow plus this and capacity. Okay. And then I'm just going to have a method. Basically, we are going to have 3 more helper method. The first is the public get other vertex or get other, which is going to get the other vertex. As you can see, we have a from vertex and the target vertex. And we just get a vertex. We don't know whether it is the starting vertex or the target vertex. Okay, so we just have to check it. If the vertex is equals to the from vertex, then we just have to return the target vertex because we get the other. And else, we just have to return the from vertex. Okay. And of course, it's going to return with a vertex. Okay, then we are going to have 2 more methods. The first is a public double get residual capacity, and we get the vertex. So basically, if the vertex is equal to the from vertex, we are just going to return with the flow, and else we just return with capacity minus the flow. What does it mean? We would like to get the residual capacity. We have been talking about that whenever we create the residual network from the original flow network, we have to consider the original edges. And we are going to create forward edges and backward edges. We have been talking about how to construct the residual network. As you can see, for example, we have an edge in the original flow network with flow 1 and capacity 4. How do we construct the residual network? As you can see, we are going to have 3 more flow. So basically, we are going to have a forward edge with the capacity minus the flow. 4 minus 1 is equal to 3. And we are going to have a backward edge with the value of the flow in the original flow network. So that's why this is the flow. What does it mean? That this is the backward edge. And we have this capacity minus flow. This is the forward edge. This is how we construct the residual network. Okay. And then we have another method, public void add residual flow to, because we have to specify a vertex, that what given vertex we would like to add the given flow. And we would like to specify that what flow is going to be added to that given edges. So it's going to be the delta flow. And if the vertex is equal to the from vertex, basically this is the backward edge. So the flow is equal to the flow minus the delta flow. We just have to get the flow minus delta flow because this is a backward edge. Else we know that this is a forward edge, so the flow is equal to the flow plus the delta flow. Okay, basically why I'm just going to save it, Ctrl-Shift-F to auto format, because this is how we calculate. We have to calculate the flow in the residual network, that what's going to be this delta flow that's going to be added. This is the forward edge. Okay, because in the algorithm, we are going to update basically the flow network and the residual network at the same time, because it is much more efficient to do so. So first we get the residual capacity, this is how we get it, and basically without constructing the given residual network, we don't have to set up, for example, and instantiate new vertices and new edges for the residual network. Okay, that we have discussing it like this in the theoretical section, but we are get all the parameters of the residual network according to the flow network's edges, because we know that the backward edge will have the flow, the forward edge will have the value capacity minus flow, and we know for certain that we have to add the residual flow to a backward edge or a forward edge accordingly. Okay, so this is how we implement the edge class and the vertex class. Thanks for watching.